All right. So this video is the Unit 6 study guide for the Unit 6 test. So you are most likely watching this informative, and you should pause when it says pause to complete the questions and type them in. Even if you're not watching this on the formative assignment, please make sure to pause and complete the questions on the test review side. So we are going to go through the in-class review side of this. And then you will have the opportunity to determine, how do you feel on this material? And then you will go through and do the test review questions, okay? So that's kind of how today's going to go. So the first objective is to identify key features of exponential functions. So first one says to describe the transformations from the parent function and the key features listed. So we have best learned to do these by graphing. So I'm going to pull up my Desmos scientific or graphing calculator here. And then I'm going to go ahead and start by graphing this function. On the test, you will have the graph to this function, but for the practice, you'll need to make sure to graph them. So remember, when you put more than just an x in the exponent, you need to put parentheses around it to make sure the entire thing stays in the exponent. But now we have our curve that popped up. So we have some things to figure out. So when we are looking for the horizontal asymptote, we're looking for that horizontal line that our graph gets really, really close to, but never crosses. Remember, horizontal is side to side, and that's going to be a y equals equation. So here, if we zoom in on our graph, we can see that our red line is going to get really, really close to y equals 1, but then never cross it. And we do have a y-intercept, so place where it crosses the x-axis. It's at 0, 10. And then since our horizontal asymptote is above the x-axis, we actually don't have an x-intercept, so we would put none. It's really important that you put none instead of 0, because if you're putting 0, it's going to make me think that there's a 0, an x-intercept at 0. Lost my train of thought there. And then for domain, we're looking for all of the possible x values, which for every exponential function is actually negative infinity to infinity. And then our range is going to be from the horizontal asymptote and everything above. So our horizontal asymptote starts at 1, and it goes up from there. So it'd be from 1 to infinity. Remember that if it was flipped and it was below, then we would write it from negative infinity to whatever our horizontal asymptote number was. And then we also need to describe the transformations. So if we're looking here, we have a plus 2 and a plus 1. There are transformations. So plus 2 tells us that it's going left 2 units. And then the plus 1 tells us it's going up 1 unit. The 3 itself is not a transformation because that's just telling us the type of exponential function it is. 3 is the base. Okay. We can also be asked questions about if it's exponential growth or, in this case, exponential decay. So we look at the b value to determine exponential growth or decay. If b is greater than 1, it's a growth function. And if b is less than 1, it's a decay function. And not necessarily less than 1, but specifically if it's between 0 and 1. It doesn't matter if it's a fraction or a decimal. It can be either. So I'm going to go ahead and just highlight all of the b values that we'll be looking at, because it's not the number that's in front. Well, this is not a great highlighter, but that's okay. So I highlighted all the b values. So we're looking at 2. So is 2 a decay function? Is 2 less than 1? No, that one's not 1. 1/2 is less than 1, so that one would be decay. 1/3 is also less than 1. 6/5 is not less than 1, but -7 times 0.1 is less than 1. So that's all we need to do. If you don't remember that rule, you can graph them in Desmos, and you can look and see if the function is getting bigger the entire time or if it's getting smaller. The only time that you can't tell that way is if it's been reflected over the x-axis. If it's reflected over the x-axis, then you have to flip whatever rule you already had in your head. So, now we're looking at the next one. So it says write an equation of a function ks that is a transformation of this parent function and is reflected over the x-axis and shifted up 4 units. So we're going to start with kx equals, and I know it's going to be 2. If it's reflected over the x-axis, then I have a -2 that's in front, or a -1 that's in front of the 2. I don't have anything that's adding or subtracting to my x because the x, or what's in the exponent, moves it left or right. And it doesn't say anything in our question about it moving left or right. But we do want to move it up, so we have to add +4. If you're having trouble remembering these transformations, make sure to take a look at your transformations note card where we wrote down what A, H, and K did. Okay. So next, now I guess would be the time. Go ahead and pause. Identify how you feel about the 3 questions we just did, and then take a moment to look at the other 3 questions. Put your answers in formative to check them. Okay. All right. So objective 2 now. This one we want to write and evaluate log expressions. So we were using the log rule, where if we have log of b of a, when we type that into the calculator, we want to type it as log of a divided by log of b. So in this case, that would be log of 7 divided by log of 49. So I'm going to open up my scientific calculator now. And remember, we can find a log on the function screen. So I'm going to put log 7 at the top, hit divide. Oops. Not fraction, I just hit divide. There we go. And then now I want to put log of 49. Okay, so that's 0.5. And remember, if it's a long decimal, we want to round to the thousandths place. So 3 numbers after the decimal point. Then we have log 8 divided by log of 1/2 for the second one. So same thing. I can keep what's there already. I'm going to put 8 up here. And then now is probably when I want to hit the fraction bar. And I want to do 1 divided by 2. And we get a -3. Perfect. So we didn't have to round either of those, but that is how we change the base of a function and evaluate a log. So if you haven't already, go ahead and identify how you feel about this, and then evaluate the 2 logs on the left side, or the right side here. All right. So our next objective is to identify the key features of a log graph. So again, on the test, I'm going to give you what the graph looks like, but we'll need to graph these here today. So I pull up my graphing calculator, and when I graph the log, I want to go to functions. Then there's a button down here that says log A. So that's going to allow me to put 2 as my base, and then to put x minus 3 in my argument, and then plus 1. Okay. So we have our graph here, and this time we're looking for a vertical asymptote. So a vertical up and down line that our graph gets really, really close to, but never crosses. So here, I can see that line kind of looks like, I can even zoom in if I'm not sure, looks like it's coming really close to 3, but never crossing 3. So I have a vertical asymptote at x equals 3, because vertical lines are written as x equals lines instead of y equals lines. So that means that a log doesn't have a horizontal asymptote. Only exponentials have horizontal asymptotes, and only logs have vertical asymptotes, from what we've learned so far. So next I see a x-intercept here at 3.5, 0. I don't see a y-intercept. There's nowhere where my curve crosses the y-axis, so I would put none. And then our domain and our range switch for the log function, because if I zoom out, I don't have anything that is bounding or confining my function up or down, which is what my range talks about. So my range would be negative infinity to infinity. But I do have a restriction from side to side, because it never crosses the line x equals 3, but it's going all the way to the right. So all the way to the biggest x value, positive x value that you can think of. Okay. So let's look at our next log that we've been given here to describe the transformations. So transformations are similar to how they are with exponentials. So whatever's inside is going to move it left or right. So inside, we're moving 2 units right. Whatever is added or subtracted outside, it's going to move it up or down. So this one's going to move 6 units up. And then we have a 1/2 that it's being multiplied by. So it's a little bit tricky because we have to think if it's a stretch or a compression. So we're going to compare it to 1. 1/2 is less than 1, which means that we have a vertical stretch by 1/2. Okay. So this was looking at key features and transformations of log functions. So go ahead and identify how you think you feel on this topic in the middle, and then pause the video and complete the test review questions on the left-hand side or the right-hand side. All right. Now is where we get to the properties of logs. So remember, we had 3 properties of logs, and we can write these in the middle as a little bit of a reference for us. So the first property that we can have is the product property. So this says when we have 2 logs that are being added together, we can rewrite them as 1 log with the products being multiplied to each other. We can also have 2 logs being subtracted. And when we write those together, we write it like they're being divided. Okay. Next, the last one is we can have n in front, and that gets moved onto the x as an exponent. Okay? So, we're going to apply that here, and when we're expanding, it means we want to take a log that's been all put together, and we are going to write it separately. So here, when we expand, we start by separating the logs by either plus or minus signs first, and then we deal with any exponents. So since I see that the x squared and the y squared are being multiplied to each other, I'm just going to put a plus sign in between those logs. So it's log base 4 of x squared plus log base 4 of y to the third. Then I'm going to take the exponent and put it in the front of each of those logs. So I have 2 log base 4 of x plus 3 log base 4 of y. So I have no exponents, and it's as expanded as it can get. So I'm going to leave my answer like that. Okay. Same thing with the next one. I do see that we have a number here, though, right? We have a 2 instead of a variable. So what I'm going to do here is I'm going to treat the 2 like its own variable, like it needs to be a separate log from everything else. So I have log base 5 of 2. And the x squared I see as being multiplied by that. So I have plus log base 5 of x squared. And then I have again plus log base 5 of y to the third. And now I have exponents that need to be moved in front. So I have log base 5 of 2 plus 2 log base 5 of x plus 3 log base 5 of y. So I want to double check. Everything's been separated into its own log, and there are no exponents left. So we're good just like that. Okay, so now when we condense them, we want to write them as one log, and we are going in the opposite direction. So I'm going to take the 1/2 and I'm going to put it as an exponent on the log. And same thing here. I'm going to put the 2 on the exponent of, or as the exponent of x. In case you forgot, if we have something that has a 1/2 exponent, that's the same as saying the square root. So in this case, it's asking for the square root of 81, which is 9. And then because I see a minus in these, when I put them together as one log, I'm going to write them as a fraction. So log of 9 divided by x squared. Because anything in front of the fraction goes in the numerator. Anything in front of the minus sign goes in the numerator. Anything after the minus sign goes in the denominator. Okay. Alrighty. So, part D, same thing. We are going to take the numbers in front and put them as an exponent of each variable or each term after the log. There isn't one, so I just have log 7 and then minus log y to the third. So there's a plus sign between the x to the 5 and the 7. So I'm going to multiply those together. Okay. And then, since I now have a minus sign, I write it as a fraction. Perfect. And that is all condensed. All right, so for a final question in this objective, we're given some logs and asked to find which one has a value greater than 1. So this is using that change of base that we used before, where log b of a becomes log of a divided by log of b. So I can type each of these into my calculator. So I'm going to do log of 4 divided by, got it backwards. Log of 2 divided by log of 4. That's 0.5, not a value greater than 1. Then I have log of 16 and log of 2. 4, that's greater than 1. Okay, and then I have log of 125 divided by log of 25, 1.5. That one's greater than 1. Log of 12 divided by log of 100. That one's definitely less than 1. Log of 9 divided by log of 1/3. It's -2. And then lastly, log of 625 divided by log 5, which is 4. So if we were just looking at this and looking to maybe try and see something similar between all of the 3 that we circled that have a value greater than 1, we can say that for each of those, the a number is bigger than the b number, and neither of them is a fraction. So that's always going to be true when a is greater than b, but neither is a fraction. Then great, it's going to have a value greater than 1. If there's a fraction in it, it's always good to just plug it in and see what you get, because fractions have different rules. But we can say the reverse too. If the base number is bigger than the argument, or the a number, then it does have a value less than 1. Okay. So I'm actually going to stop the video at this point, but you should go ahead and, I don't even know where my file went, but go ahead and determine how you feel about the couple of questions that we just did in this objective, and then make sure to complete the test review questions. There'll be another follow-up video to help you complete the rest of this study guide.